This is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to today's lecture. In this lecture, we'll discuss about the excitation tables of all the flip-flops. So, as we all know about the flip-flop. So, flip-flop is a basic building block of sequential circuit. So we have various types of flip-flops. Those are SR flip-flop, JK flip-flop, D flip-flop and T flip-flop, where the flip-flop can also be used as a memory element which can store one bit of information at a time. So now we are going to discuss the excitation tables of all the flip-flops, where these excitation tables will be used while converting one flip-flop to the other flip-flop, and also while designing sequential circuits like counters and registers. So, we'll be discussing the excitation tables of all the flip-flops. So, what is an excitation table? So, excitation table has the minimum inputs which will excite or trigger the flip-flop to go from its present state to the next state. That means, we can say in another way, the excitation table will give or else will show the possible inputs that needed to be applied to the flip-flop in order to change its state from present state to the next state. So here, these excitation tables are derived from the truth table. So we all know the truth table. So what is a truth table? So generally the operation of a flip-flop can be explained with the help of truth table, where the truth table lists all the possible combinations of input along with the present state, so that the next state of the flip-flop can be estimated. So that means we can say that the truth table is a table representation of flip-flop with which we can decide the next state of the flip-flop for the present input, present state, and the inputs applied at that particular time instant. So the truth table lists all the possible combinations of input for which we will be able to identify or else produce the next state of the flip-flop or else the output of the flip-flop. Next, the excitation table consists of two columns, one for the present state and one for the next state. So, based on the present state and next state, we will be deciding the inputs that are to be applied or else the excitation that are to be given to a flip-flop to achieve the transition from present state to the next state. That means the excitation table consists of columns, that is present state Qn and next state Qn plus 1, and the inputs needed to be applied to achieve the transition from present state to the next state. So here one thing we have to remember, the number of inputs will be varying depending on the type of the flip-flop. For example, if we are taking SR flip-flop and JK flip-flop, we have two inputs, SR and JK. Whereas in case of the other two types of flip-flops, that is D and T, we have only one input. Whereas the present state and next state columns are common to all the types of flip-flops. So this is the major difference between the truth table and excitation table. So in truth table, in short, the truth table will be having the inputs and the present state from which we can estimate the next state of the flip-flop. And in excitation table, we will have the present state and next state, and according to that, we will be deriving or else we will be identifying the inputs or else excitation that must be given to the flip-flop to get a transition from present state to the next state. Now, so that is about truth table and excitation table. Now we'll derive the excitation tables of all the flip-flops one by one. Now first of all, we'll discuss the excitation table of SR flip-flop. So here, in order to achieve excitation table, not only of SR flip-flop, of any type, we need to have truth table. That means the excitation table of SR flip-flop can be constructed from its truth table. So here, the truth table of SR flip-flop is as shown. So, as I told you, in truth table, we'll have all the possible combinations of input for which the next state of flip-flop can be decided. So here, if we look at this truth table, so S and R are the inputs, and the next one is present state, which is also considered as input here. So these are all the inputs, whereas this one is considered as output. So which is the next state of flip-flop. So as this is a sequential circuit, so we all know that the sequential circuit, the next state depends on the present inputs and also the present state. So here SR and QN are the inputs, whereas QN plus 1, which is the next state of the flip-flop, is considered as output. So here already we know that the SR flip-flop truth table, so SR, so QN plus 1. So if S and R are 0, 0, then the next state is equals to the present state of the flip-flop. Next, if S is equals to 0 and R is equals to 1, irrespective of the present state, the next state of the SR flip-flop will be 0. This means R input, that is reset input, is 1, and hence which resets the flip-flop here. Resetting means making the output 0. Next, if S input is 1 and R input is 0, irrespective of the present state, the next state of the flip-flop will be 1. That means the flip-flop will set to 1. Next, if it is 1, 1, we have indeterminate state. We have indeterminate state. Indeterminate state means we are not able to identify the next state of the flip-flop where the Q and Q bar are becoming equal, where the Q and Q bar must always be complement to each other. So this is a truth table. Now, based on this, the truth table of SR flip-flop, extended truth table of SR flip-flop is this one. So here I am taking S and R as 0, 0 and the present state as 0, 1s and 1, 1s. So if the S and R inputs are 0, 0 and the present state is 0, the next state is equals to 0 because there is no change in the state. So we can also call it as no change, and this is reset and this is set. So that means the flip-flop will not change its state if S and R inputs are equals to 0, 0. Next up. So here that is why as SR 0, 0, present state is 0, so next state is also 0. SR 0, 0, present state is 1, so the next state is 1. Now coming to S is equals to 0 and R is equals to 1. So according to this truth table, so when our reset input is 1 and set input is 0, whatever it may be the present state, the next state is equals to 0. That means it resets the flip-flop. That is the next state is equals to 0. So in both the cases 0, 1 and the present state 0, the next state is 0, and 0, 1, present state is 1, so the next state is also 0. Next up, if the reset input is 1 and the set input is 0, set input is 1 and the reset input is 0, then it sets the flip-flop irrespective of its present state. So whatever it may be the present state, the flip-flop will set to 1. Next 1, 1, whatever it may be the present state, it will be considered as indeterminate state, and the indeterminate state is represented as don't care. So this is the flip-flop, SR flip-flop truth table. Now, how to derive the excitation table of SR flip-flop? So as I told you, excitation table is derived from the truth table. Consider the truth table here, SR flip-flop. And now, from this, we are going to derive the excitation table for this one. So here, as I told you that in excitation table, we will be having the Qn and Qn plus 1, which is the next state, present state and next state. For that, we are going to decide the inputs to be applied to the flip-flop. So this is the excitation table of SR flip-flop. So how we have got this one? So here I have shown in different colors. So which leads to, so here present state and next state, as we have two variables here, we will be having 4 combination. If the present state is 0, next state may be 0. If the present state is 0, next state is 1. And if the present state is 1, next state may be either 0 or 1. So that is why 1, 0, 1, 1. So these are all the possible combinations for present state and next state. Now from the truth table, we are going to find the values of S and R such that the transition from present state to the next state are defined one here. 0, 0. If the transition is from 0 to 0, what must be the inputs given to the S and R? So now, for that, go through the truth table here. Now, first, if you observe S is equals to, Qn 0 and Qn plus 1 0, present state 0 and next state 0. So, verify the combinations of S and R for which the present state is 0 and next state is also 0 in the truth table. So if you observe, the yellow color ones rows represent the present state is 0, next state is 0. So here if you observe this one, this is also present state 0, next state 0. And if you observe the S and R inputs here, S input is 0, and for the first one, S input is 0 and R input is also 0. Next, for the second one, S input is 0 and R input is 1. So that means here the flip-flop is taking a transition, SR flip-flop is taking a transition from 0 to 0. That means if the present state, next state is 0, from the present state 0, when S is equals to 0, R is equals to 0 and S is equals to 0, R is equals to 1. So if you observe these two combinations, S value is common, which is 0, whereas R value is varying, either 0 or 1. So R value is not constant here. So we can represent R as a don't care. So that means S is equals to 0 and R is equals to don't care. The transition in the flip-flop is from 0 to 0. That means the present state is 0 and next state is 0. So this is to be filled in the first column of the excitation table. Okay. So that is why the first column of excitation table is filled with 0, don't care, where the transition from present state to the next state is 0 to 0. Now, next condition. What is that? Present state is 0, next state is 1. And look for the inputs for which the present state is 0 and next state is 1. If you observe light color one, so this one is having a transition of present state as 0 and next state as 1. And one more is there. So this one is also okay. So here this is having 0 to 1 transition. This is having 0 to 1. No other combinations are having a transition of 0 to 1 if you observe the truth table. So in this case, so only this combination of S and R will leads to present state 0 and next state 1, wherein S is equals to 1 and R is equals to 0. So that is why the second row of this excitation table is filled with S is equals to 1 and R is equals to 0. Next one. Next column is 1, 0. If you observe, Qn is equals to 1 and Qn plus 1 is equals to 0. So Qn plus 1 is equals to, so if from the truth table, we can see that this is having present state as 1 and the next state as 0. And in this case, the inputs applied are S is equals to 0 and R is equals to 1. So that means we need no other combinations are producing the present state as 1 and next state as 0 if you observe the truth table. So that is why we can fill the third row of the excitation table as 1, 0. So the SR inputs are 0, 1. So this is the next one. Next up, 1, 1. Next one is present state is 1, next state is 1. So if you observe the truth table, we have this combination for which the present state is 1 and next state is 1, where the input S is equals to 1 and R is equals to 0. And we have one more combination which is producing the present state as 1 and next state as 1, in which S is equals to 0 and R is equals to 0. So if you observe these two, R value is common, which is equals to 0, whereas S value is varying, that is either 0 or 1. See, if R is equals to 0 and if S is either 0 or 1, then we will be getting the present state and next state as 1, 1. So I am writing S as don't care. So for present state 1, next state 1, the inputs that must be given to the flip-flop in order to achieve the present state, or else a transition from 1 to 1, that we need to apply the inputs as don't care, 0. S must be don't care, that means S must be either 0 or 1, whereas R must be a constant value which is equals to 0. Then we can get the transition of flip-flop from present state 1 to the next state 1. So this is SR flip-flop, and here these are the last two columns which are shown in red color are called as invalid states, or else we can also call it as indeterminate state, where S is equals to 1 and R is equals to 1. So coming to the summary here, for the state transition from Qn is equals to 0 to Qn plus 1 is equals to 0. That means the present state 0 and the next state is also 0. The inputs that must be applied to the flip-flop, SR flip-flop, are S is equals to 0 and R is equals to either 0 or 1. And hence, we are filling the first row. That means we can identify the inputs that must be applied to the flip-flop in order to achieve this transition as 0, don't care. Okay, where S is equals to 0 and R is equals to don't care. Next up, to obtain the next state output Qn plus 1 as 1, from the present state Qn is equals to 0. That means here Qn is equals to 0 and Qn plus 1 is equals to 1. So this can be achieved by applying the input S is equals to 1 and R is equals to 0. Qn plus 1 is 1. Means what? We are setting the flip-flop to 1. That means this can be done when the set input is 1 and the reset input is 0. So set input is 1 and reset input is 0. Next, coming to the third condition, when we need to have a transition from 1 to 0. That means if the present state is 1, I want to go to the next state as 0. That means what I am doing? I am resetting the flip-flop. Resetting can be done when R input is equals to 1. And hence, the inputs that must be given to the flip-flop in order to have a transition from 1 to 0, then the inputs are S is equals to 0 and R is equals to 1. And similarly, for a transition of flip-flop from present state 1 to the next state 1, we need to apply the inputs to the flip-flop such as S is equals to 0 and R is equals to 0, and one more combination, S is equals to 1 and R is equals to 0. So as S value is varying, so we can write that S as don't care, and hence we can say that in order to have a transition from 1 to 1, S must be don't care and R must be 0. So this is the excitation table of SR flip-flop. Now coming to the JK flip-flop, excitation table of JK flip-flop. So here again you know that in order to achieve the excitation table of JK flip-flop, we need to have the truth table of JK flip-flop. So the truth table of JK flip-flop is as shown here. So we already know that the JK flip-flop truth table we have when J is 0, 0, 0, 1, 1, 0, 1, 1. When J and K are 0, 0, then the next state is equals to the present state. when j is equals to 0, k is equals to 1, the flip-flop will reset to 0 because k input is equivalent to r reset input, and j is equals to 1, the flip-flop will set to 1, that means qn plus 1 is equals to 1. And when this is 1 and 1, when j and k are 1 and 1, whereas in SR flip-flop we have indeterminate state which is eliminated in JK flip-flop, and in this case this output is complement of the present state. That means the next state of the flip-flop is the complement of present state. So this is the truth table of JK flip-flop. Qn plus 1 is equals to Qn complement when j and k are equal to 1 and 1. So this is about the truth table of JK flip-flop. So now we are expanding that. So take JK and the present state Qn as the input, and we are finding out the next state Qn plus 1. So when the j and k inputs are 0, 0 and the present state is 0. So when jk inputs are 0, 0, next state is equals to the present state. So Qn plus 1 is equals to Qn, where Qn is 0 here, and hence Qn plus 1 is also 0. Next up, j and k 0, 0 and the present state is 1, and hence the Qn plus 1 is also equals to 1. Next up, when j is equals to 0, k is equals to 1, irrespective of the present state, as a k input is 1, the flip-flop will reset, and hence the next state is 0. That means it is reset. And here even though the present state is 1, as the k input is 1, the flip-flop will reset. Now, as the j input is 1, irrespective of present state, so the flip-flop will set. So this is set. So this is no change, and this is reset, and this is set, and this is complement of present state. Complement of present state. So now both the inputs are 1 and 1, j and k, and the present state is 1. So when both the inputs are 1 and 1, the next state is the complement of present state. As present state is 0, next state is 1. And here as the present state is 1, the next state is 0. Complement of 1 is 0. So next up. Now we are going to derive the excitation table for the JK flip-flop. Consider the truth table here of JK flip-flop, and this is the excitation table of JK flip-flop. So now again, excitation table will have present state and next state, and followed by the inputs of the flip-flop. JK flip-flop is having two inputs, j and k. Now we are taking four possible values for present state and next state: 0, 0, 0, 1, 1, 0, 1, 1. This is my present state, and this is the next state of the flip-flop here. Now we'll be identifying the present state values and next state values and their respective inputs from the truth table. So if you observe, this is the combination for which the present state is 0 and the next state is also 0. And we also have one more combination. Here this is the combination for which again the present state is 0 and next state is 0. Now if you observe the inputs here, j is equals to 0 and k is equals to 0. Next one more, j is equals to 0, k is equals to 1. This is for qn 0 and qn plus 1 is equals to 0. Right? So now here if you observe this, j is common, which is 0, whereas k is varying. So and hence I can write j is 0 and k is don't care, because k is 0 once and 1 once. So for getting a transition in the JK flip-flop from 0 to 0, from present state 0 to next state 0, we must apply the inputs to the flip-flop, or else we must give the excitation to the JK flip-flop such that j is equals to 0 and k is equals to don't care, where don't care means either it may be taken as 0 or 1. Next condition. We are checking for the next one, that is next transition from present state 0 to next state 1. If the flip-flop has to change its state from 0 to 1, then what must be the inputs applied? So now, first combination we are applying here. We are checking for j is equals to 1 and k is equals to 0. So this is the second, j is equals to 1, k is equals to 0, comma. Next up, one more combination we can observe here, which is this one, 0, 1. So this is the another combination. So which is here. Okay. So this is another combination where we can say that j is equals to 1 and k is equals to 1. So if you observe this one, j value is common, which is 1, whereas k value is varying, and hence I can write j is equals to 1 and k is equals to don't care. So that is filled in the second one. Okay. So for achieving a transition from 0 to 1, the j and k inputs must be 1, don't care. Now let us see the next one, 1, 0. So we have the present state as 1 and the next state as 0, where the inputs are j is equals to, for this first combination, which is shown in green color, that is j is equals to 0, k is equals to 1. And one more combination we can observe here, this one, where we can have qn is equals to 1 and qn plus 1 is equals to 0. In this, j is equals to 1 and k is equals to also 1. So j is equals to 1 and k is equals to 1. If you observe this one, I can write as j is varying, j is don't care, and k is common, so k is equals to 1. Don't care 1. So in order to have a transition from 1 to 0, don't care 1 must be the inputs given to the jk flip-flop respectively. J is don't care and k is equals to 1. Now the final one, 1, 1. So here if you observe this combination, we have a transition, or else we have present state as 1 and the next state is also 1. So what is the value of j and k here? J is equals to 0, k is equals to 0. And we can observe one more combination which is producing a transition 1 to 1. So here 1 to 1, where j is equals to 1, k is equals to 0. So as j value is varying, I can write j as don't care and k value is common, which is 0. So that is don't care 0. So 0 don't care, 1 don't care 1, don't care 0. Don't care, remember always, don't care indicates either it can have 0 or 1. Next up. So coming to the summary points here. So in order to have a transition from present state to the next state, such as 0 to 0, we need to apply the inputs to jk flip-flop such that j must be considered as 0 and k must be don't care. And k must be don't care. So that is 0, don't care. Next up, that here, in order to have a transition from 0 to 0, the values of j and k must be 0, don't care. Next up, in order to have a transition from 0 to 1, we need to apply the inputs to the jk flip-flop. J is equals to 1 and k is equals to 0, or j is equals to 1 and k is equals to 1. And hence we can also say that j must be 1 and k must be don't care. So to have a transition from 0 to 1, jk must be 1, don't care. And similarly, to have a transition from 1 to 0, j must be don't care and k must be 1. Finally, in order to have a transition from 1 to 1, we need to apply the inputs to the jk flip-flop such as j is equals to don't care and k is equals to 1. So this is about the excitation table of jk flip-flop. Now coming to the d flip-flop. So we all know that d flip-flop is also called as delay flip-flop. So in which, or else data flip-flop, in which the next state is always equals to the data input, irrespective of the present state. Whatever it may be the present state, the next state is equals to the data input. If the data input is 0, the next state is 0. If the data input is 1, the next state is 1. So in order to derive the excitation table, consider the truth table of D flip-flop, so which is shown here. So as I told you that irrespective of present state, if the next state is equals to the present state. If you observe that, we can from the definition I have told you, qn plus 1 is equals to d. Qn plus 1 is equals to d. So here I'm taking the input, data input, and the present state qn 0 0 0 1 1 0 1 1. So as the data input is 0, irrespective of present state, the next state will be 0. In both the cases, the next state is 0. Okay, because d is equals to 0 here. And in both these cases, d is equals to 1, qn plus 1 is also equals to 1. So now we'll derive the excitation table of D flip-flop here. So we have considered the truth table, and this is our excitation table. So now, as I told you that irrespective of present state, the next state is equals to the data. So as here we have present state as 0, we can write data input as 0. And present state as next state as 1 here, data input as 1. And because we know that qn plus 1 is equals to d. Okay, so even you can observe here. So we have 0 to 0 transition in which the input is considered to be 0. So that is filled in the first row. Next, 0 1 transition here. So where data input is 1. Next, 1 0 transition where the data input is 0. So that is filled here. Next, 1 1 transition where the data input is 1 here. Okay, so that is filled here. So this is the excitation table of D flip-flop. This is very easy because as I told you that the next state is equals to the data input. So irrespective of the present state, whatever the next state, that is equals to the data input. So here coming to the summary point. So as we have discussed here from the truth table, it is shown that the next state output is equals to the data input. So from the transition, in order to have a transition from 0 to 0, the required input must be that must be applied to the flip-flop is D is equals to 0. Next, in order to have a transition from 0 to 1, the input given to the data D flip-flop is 1. In order to have a transition from 1 to 0, as the next state is 0, D input must be considered as 0. To have a transition from 1 to 1, so the next state is 1, and hence we need to consider the data input as 1. Next, coming to the T flip-flop. So the T flip-flop is also called as toggle flip-flop, in which the operation is decided such. So again, in order to derive the excitation table of T flip-flop, we need to consider the truth table. So the truth table of T flip-flop is as shown here. So from this, we can say that if you observe the input, as it is a single input flip-flop here, we have only 2 columns here for inputs. One is T and the other one is present state. So if toggle input is 0, we can say that the next state is equals to, so I'm writing here. So this is a truth table, qn plus 1, next state. So if toggle input is 0, the next state is equals to the present state. If toggle input is 1, next state is equals to the complement of present state. So this is a truth table. As t is equals to 0 and the present state is 0, so next state is also 0. Okay, so next state is also 0, right? Because qn plus 1 is equals to qn here. Next state is 0, t input is 0, whereas present state is 1. So when t input is 0, next state is equals to the present state, and hence the next state is equals to 1 here. Next, toggle input is 1 here and the present state is 0. When the toggle input is 1, the next state is a complement of present state. What is the present state? 0 here. Complement of present state, it is 1. Next, toggle input is 1 and the present state is 1. So the next state will be complement of present state, which is equals to 0. So now we are going to derive the excitation table. So as it is also having a single input, so it is also easy to derive the excitation table. Even to remember the excitation table, it is very easy. Next, so this is the truth table and this is the excitation table of T flip-flop. So here, now, so excitation table will have the columns, present state, next state, and the inputs that are to be applied to the flip-flop. So the input that can be applied to the flip-flop is T here. Present state 0, 0, 0, 1, 1, 0, 1, 1. Now, as I told you that okay. So here the present state is 0 and the next state is also 0. Now you observe the combinations in the truth table which are having present state as 0 and next state as 0. So if you observe, this is the column where present state is 0 and next state is also 0. And for which the toggle input is 0. So that is filled in the first row. Now coming to the next one, present state 0, next state 1. So if you observe it in the truth table, so here this is the column where we can have present state as 0 and next state as 1. For which the input is, the input T is equals to 1. So that is filled here. T is equals to 1. Next up, coming to the present state 1, next state 0. So here, this is a combination where we have present state as 1 and the next state as 0, where the T input is 1. That is filled here. Next up, the last one, present state is 1 and present state is 1 and the next state is also 1. Okay, so here this is the condition which is showing us the present state as 1 and the next state as 1, in which the toggle input is 0. So we are filling it. Or else we can also see that present state and next state. Is there any change in the present state and next state? No. So as I told you that when T is equals to 0, the present state is equals to the next state. As both are same, we need to consider the present state as 0. Next up, here next state is a complement of present state. So the complement of present state can be happening when T is equals to 1. So that is why T is equals to 1. Now here the present state is 1, where the next state is 0, which is a complement of present state. This can be happen when toggle input is 1. Next, present state 1, next state 1. There is no change and hence T should be considered as 0. That means what we can observe here, in order to derive the excitation table, one should be familiar with the truth table. Otherwise, we cannot derive or else remember the excitation tables. So that is about the excitation table of T flip-flop. Now, the summary. So as we know that from the truth table, we can observe that when T input is 0, there is no change in the state of the flip-flop. That means we can say that Qn plus 1 is equals to Qn. That is, next state is equals to the present state. Next, and hence we can say that if you want to have a transition in the flip-flop from present state 0 to the next state 0 and from present state 1 to next state 1, we need to apply the input to the T flip-flop T as 0. Because in both the cases, present state is 0 and the next state is also 0. And here present state is 1, next state is also 1. So in order to not to have a change in the state, we need to consider T must always be equals to 0. Similarly, we can also observe one more thing. When T is equals to 1, the present state is complemented. That means the next state is a complement of present state. And hence, we can say that to have a transition from present state 0 to 1 or from 1 to 0, we need to consider, or else we need to apply the input to the toggle flip-flop, that is T input. T must be equals to 1. So that is 0 to 1. So that means it is Qn, whereas this is Qn plus 1, where both are complement to each other. That means Qn plus 1 is a complement of present state. So this can happen only when the toggle input is equals to 1. So this is about the excitation tables of all the 4 flip-flops. As I told you that these excitation tables are used in the conversion of flip-flops from one to another, and also in order to design sequential circuits such as the counters and registers. Even in sequence counters we have, that is, even in sequential circuits we have synchronous sequential circuits and asynchronous sequential circuits. So to design the design of synchronous sequential circuits and asynchronous sequential circuits, we will be using these excitation tables, and hence you must be familiar with this excitation tables. I hope it is clear to everyone. That's all for this lecture. Thank you, one and all.
Like, share and subscribe. Hit the bell icon for more updates.